In the middle of a rather large project. What I'm doing is I'm trying to program a manual computer, i.e. one without any electronics in it, to be able to beat me at quite a simple game. So at the moment the computer doesn't have any skill at all in the game, and over the course of playing me it's going to learn. It's an example of computer learning. I got this from an article by Martin Gartner, which is all they ever seem to do at the moment. And around me in my library I'm surrounded by the computer. So let's switch to the back camera. The game is called Hexapawn. I'm going to be playing as white and the computer is going to be playing as black, and these pawns move just like pawns do in normal chess. So they move forwards, one space forwards, but they take diagonally. White moves first just like in normal chess, and you can win the game in one of three different ways. You can win it by taking all the other pieces, by getting one of your pieces to the other end of the board, or, and this is different from normal chess, if you don't have any available moves to you, then you lose the game. So there's no stalemate in this. If everything gets shunted up and there's no moves and it's your turn, then you lose the game. Now, this game can't go on for very long. I think you definitely win by the 7th move at least. And around the room, I've got a whole lot of quite low-tech components in the computer. So all of the different positions are written on pieces of paper, are going around the room, and each one has a kind of loo roll tube, paper stuffed into the bottom, with different M&M counters, which for each of the positions match up with the different moves that the computer has available. So at the moment it's going to be kind of random. Over here, because I'm playing move 1, I'm going first, these are the move 2s for the computer. Over here we have all its possible move 4s, and the other side of the room we have all of its possible move 6s. And after that the game is definitely over. Now the computer is going to learn as we go along, and it's going to learn both by me rewarding it for playing good moves and punishing it for playing losing moves. And I think it's best done by an example. So I haven't analysed this game. I felt it would spoil the fun. So I'm just going to play one of the moves and we'll go from there. So I'm going to play this move here. Okay. Now it's the computer's turn, and to get its move we're going to go to what that position is. So notice, let's get you steady. Notice there are only 2 possible positions that we can be in after that first move if you take out all the reflections. So although there's no move the right pawn forwards, it's just the same as this one over here, which is what I ended up playing anyway. And so this suffices. There are only 2 essentially different moves. Okay, now there are 3 different moves that the computer can play. There's an orange move, a green move, and a blue move, and it has no preference for them. In here we have an orange, a green, and a blue. So what we're going to do is I'm going to randomly shake one and take one. Whoop. And it's blue. So it's going to play the blue move. It's going to move its left, so my right, pawn forward 1. Over here, it's played this move. And I can see that I've got a winning move now, because if I do pawn takes pawn, then I've got to the end of the board and I can promote. Now that was a losing move for it, so what we're going to do is we're going to confiscate this thing here. Okay, right, let's go again. So that computer will never play that move again. It knows that's bad. Well, that went quite well for me, so I'm going to do the same thing. I'm going to move this forwards. So we're going over here. And what have we got? Yep. It's a green. So I'm going to leave that there for a minute. It's moving the central pawn forwards 1. Like that. Now I can't win this move. Oh, I can. Here we go. Ta-da. So now the computer is lost because it doesn't have any legal moves. So we're going to confiscate it again. Now one thing I haven't been doing so far is tracking its wins and losses. And I'm hoping that it's going to start off losing quite a lot at the start, but on my big board of Alaric versus computer, which is quite an ego boost, I've got Right and left-handed, so I've got Alaric for the first two games. Okay, let's go again. Reset. Right, ta-da. Well, actually, it's only got one move left now, which is orange. Okay, so it's going to do pawn takes pawn. Right. Well, I'm going to try taking, I think. Okay. So we're in this position, so now we've got to go to the move fours. And we've got to match up whichever position it was, which happens to be this first position here. Now, in this position, there's only one move it can do, which is why there's only one M&M in there. But let's go through the process anyway. We've got a blue M&M, which is move the pawn forwards. Ta-da. Now I have no legal move, so I've lost the game. Okay. Now what we do to reward it when it's won the game is we're going to double up its M&Ms in the winning track. Now, so we need one orange and one blue. So the blues go in there, they've doubled up. The oranges go in here, they've doubled up. Now because each of these didn't actually have any other colours in there, it won't affect the probabilities. But you get, for ones where there were multiple colours within there, and that will be true a lot of the time, it will give you a weighted average, so it's going to win more of the time. The process, if there was quite a long string of moves and then a loss, is you only confiscate the last M&M. I'm going to carry on playing this many times and listening to lots of podcasts. I'll get back to you in a bit when I've played a few more. Okay, I won 4 in a row. So going left to right, it's going through time, and under it is what move either I or the computer won on. Notice that I'm always going to win on an odd move, and the computer is always going to move on an even move. And I thought it would just be interesting to see the length of the game creep up as we go along. The computer isn't yet perfect, but is winning most of the time, and it should be a one game for black. I thought we'd just go through one game. So let's have a go. Right, so I'm going to try going in the centre. It's mostly figured out the edge move now. Now both of these ones over here, I've stopped doing all the duplicates in them because there's only one move there. So we're in this one here, and it's going to go red. So it's completely got the second move sorted for each of my initial things, which is taking. Okay, now I've got a bit of choice here. Each pawn can either take or go forwards. I haven't yet explored all the things against the computer. I'm going to try doing this one, which I've done a few times, sometimes winning, sometimes losing. So this position over here will be move 4 for the computer. And it's this one here. If we just look at the distribution of these so far, it's one doing the blue move once before, but the rest it hasn't tried yet. Yeah, that's true. So if we try doing that, take one at random, it's going to try the red move this time. So it's going to try going forwards. So let's go at that. Going forwards over here. Well, I'm going to try taking. And I've won. So let's go and eat that red one. Oh. So it's Alaric, and it was the 5th move. So it's not yet perfect, but it's certainly winning more of the time than it did at the start, and it's definitely not losing on the first goes as it was before. I just want to talk a bit about the versus reward aspect of this. So it seems that the punishment is more crucial because it stops it losing immediately. But the reward means it wins more games over a shorter time period. What it does mean as a disadvantage is it takes longer to become perfect, because it's taking some of the time to promote moves which aren't going to win overall. So if you want a computer to win the most games over, say, 25 games, you want reward as well as punishment. But if you want it to get a perfect in as short a time as possible, you just want punishment, which is strange. I'm going to go a bit more. He's winning almost all of them now. Notice I did get one more win, and looking at the internal workings of the computer, it is still possible to win. It's just it happens so little of the time. Let's just have a look at what some of the pots are doing. So, okay, first off, here's one of the kind of phenomena. Here is a position where blue has been got rid of long ago, because that was a losing move for it. Both orange and red moves are ones which win in this position. The orange move by promoting and the red move by removing all my pieces from the game. But once one strategy starts winning, it keeps getting promoted, and so it wins most of the time. And so you've got this kind of feedback loop of a computer having a preferred strategy, even though others might win. So let's put those back in. Another weird thing that the promotion has been doing, if I take you over here, let's look at this one. So, let's just analyse the moves first. We've got orange promote straight away winning. The other ones don't win immediately. And in fact, if you look at red, it's a losing move, because if it pushes the red move, then I can take, or I can promote, or I can promote in 3 different ways. But if we look at what's happening here, it kept winning by promotion in different ways. So it still has the red there. It is still possible for me to win, but it won by orange once, it won by blue once, and it won by green lots of times. And not all of those moves lead to instant wins, but all of them on the move 6 on the other side of the room, they've been promoted to win all the time. So the red is the only way I'm going to win. But for it to become perfect, it needs to eventually draw the red, which is getting it less and less likely over time. So by having this promotion of moves, this reward system, you make it so it takes a very long time until the computer is perfect. But it does mean it wins a lot quicker than a computer which is only having algorithm is called a genetic algorithm. It has generations. Each one is producing a better system, and I just really like them. It's using evolution as a mechanism for improving a program. So it's randomly changing. There is no actual thought being put into it by the computer. All the thought is being by the environment, which in this case is me. So the better the player, the quicker it will learn. If you play lots of stupid moves against it, it will start promoting moves which aren't as good long term. But if you play only perfect moves against it, it will get quicker, better. And people use these sort of algorithms to do things like chess. And I'm doing it manually, but if you program this up, you could do much more complicated games. And if you had 2 systems of this, and you could play them against each other. So if you program one of the same thing to do moves 1, 3, 5 and 7, then you could have 2 algorithms, 2 computer systems, both improving off each other. And people do this sort of thing for chess. And if you have computing power, you can just do thousands of these per minute, playing computers against each other. They're playing rubbish moves at the start, and they get better and better. Now, we haven't been able to, like when we talk about solving a game, with this sort of game we can solve it explicitly. We can know for each move what to do. And so, for example, things like checkers and drafts, we have solved that game. Or slightly less complicated noughts and crosses, well, definitely less complicated, we've solved. But something like Connect 4, we've solved as well. Whereas if we consider things like chess and Go, we don't have the best answer for every situation. We can solve chess with 7 pieces on the board or fewer, but we start off with 32 pieces, and we haven't yet got there. And in fact, it looks unlikely, just by the sheer number of positions, that we will be able to do that. Go is even more complicated. You start off with a 19 by 19 board, usually, and so on the first move you've got 19 squared possibilities. For the second move you've got 19 squared minus 1 possibilities. It is a much bigger state space than, say, this game we've been playing here today, Hexapawn, which at most I think is 7 moves, maybe it's only 6. You can never get that. It's 5, I don't know. But it's a much smaller state space, so you can complete the algorithm with this sort of thing. Genetic algorithms don't seek the best solution. They only get a solution which fits the parameters that you're trying to get, kind of tending towards maximility, rather than actually getting there. So I've created a system which can consistently beat me, but isn't yet perfect. But I'm not going to play it anymore. You could, if you wanted to, and if you had many more loo rolls than I have, or if you have computing ability, then you can do this for more complicated games. So Martin Gartner suggests doing it with drafts played on a 5x5 board. Each person starting off with 3 checkers in it. But yeah, cool. I'm having quite a lot of fun preparing these. At the moment I'm sorting all of these into 2 colour bowls. So greens and browns, reds and blues, these are going to be yellows and oranges. This is the preparation stage. Yes. If you're not going to use them for some sort of mathematical experiment, I recommend this as just a very satisfying thing to do in life. I don't even like M&Ms.